Hello again. Today we're going to be talking about how to represent functions as power series. So let's get started. We're going to go through as many examples as I can think of that represent things that you might be asked on the AP test. So let's get started with a simple one. We have f of x. It's an infinite series. Every term looks like x to the n over n to the third. We're starting at n equals 1 and we're going to infinity. So if we write out the first four terms of this series, then the first term is just going to look like x to the n over n cubed, but n is replaced with 1. And in the second term, every n is replaced with 2, so we get x squared over 2 to the third, and so on. Just with every term, they only wanted the first four. I can simplify each of those if I wanted to, just in case I was using it for something else. So x to the 1 over 1 cubed could just be x. X squared over 2 to the third could be x squared over 8, and so on. All right, so that's just an example of that. The next thing I might be asked for is the interval of convergence. And we've talked about this before. This is where you use the ratio test and you set it to be less than 1. So just to remind us of what the ratio test is, we're going to take the limit as n goes to infinity of the n plus 1 term over the n term. And we're going to set that to be less than 1. So if I take the n plus 1 term, that's just going to look like the n term, but every n is replaced with n plus 1. So I get x to the n plus 1 over n plus 1 cubed. Then if I'm dividing by the n term, I can just take the n term as it is in the general term up there and flip it upside down and multiply instead. So I take the absolute value of that, and I'm just going to group the things together that are like each other. So x to the n plus 1 over x to the n, that's going to reduce to just x. And then if I look at n cubed over n plus 1 cubed, those both have the same degree. So as n goes to infinity, I'm just going to divide those lead coefficients. That's going to be 1 over 1, which is just 1. So the whole thing reduces down to x. I don't need the limit anymore because there aren't any n's in that expression x. So I'll just set the absolute value of x to be less than 1. That means that x has to be between -1 and 1. So that's where I start. But remember, I have to check those endpoints, -1 and 1. And to do that, I'm just going to plug them into the series that is right there at the top. I'm going to replace x with -1, and that's what it's going to look like. I need to recognize that that is an alternating series because of the -1 to the n. So for an alternating series, I need to answer two questions. The first question is, do the terms reduce in size? Well, as n gets bigger, n cubed is going to get bigger, and those fractions are going to get smaller in size. So that's the first requirement. And if you plug in various values of n and you watch what happens as n gets bigger, those terms are going to approach 0 in size. So both requirements have been met. So I can include -1 in my interval of convergence. Then if I plug in 1, I don't have an alternating series anymore. All the terms are positive, but it is a p series. And the value of p, that's the exponent of n in the denominator, that's 3. It only needs to be bigger than 1, and 3 is bigger than 1, so that p series does converge. So I can include 1 in my interval of convergence as well. That means that my interval of convergence, it goes from -1 to 1, including -1 and including 1. Okay. Next part of that same example, we're going to write the first four terms in the general term of the derivative of f. So let's remind ourselves what f of x looks like. I've included the general term in there as well. So taking the derivative of x is going to give me 1. Taking the derivative of x squared over 8 is going to give me 2x over 8, and so on. And all of those can be reduced. So 1 is fine the way it is, but 2x over 8 can be x over 4. 3x squared over 21 or 27 can be x squared over 9, and you can just reduce all of those terms, including the general term. All right, for the second example, we've got specifically the Maclaurin series for e to the x. It looks like that. If I wanted to write the first four terms in the general term of e to the 2x, that means every x on the right-hand side of the equal sign is going to be replaced with 2x. In parentheses, just so that I know that the exponent applies to both parts of it, the 2 and the x. So that's what it's going to look like. I just replaced every x with 2x, and that's what it looks like. The next thing I might have to do is write out the first four terms in the general term of x times e to the x. This is a little more involved because now I'm taking x and I'm multiplying it by every term in that series. So I distribute that x to every term in the infinite series. And what that does is it makes the 1 into an x, it makes the x into an x squared, and it basically raises the exponent of every term by 1. So that x to the n over n factorial becomes x to the n plus 1 over n factorial. Same example, same series, but now we need to write out the first four terms in the general term of e to the x minus 1 over x. So let's start with the numerator where we have e to the x minus 1. All that means is that the first term is gone. I'm subtracting that one term. So the new series starts at the second term, which is x, and it includes all of the other terms after that. So that's what it looks like. So to divide by x now is kind of similar to when we were multiplying it by x, but instead of raising the exponent of x by 1, we are now lowering the exponent of x by 1. So x squared over 2 factorial just becomes x over 2 factorial. X cubed over 3 factorial becomes x squared over 3 factorial. And in general, x to the n over n factorial becomes x to the n minus 1 over n factorial. So that's what that looks like. Moving on to a different one, now we're going to use the Maclaurin series for sine of x, as I've shown it to you there. You should be familiar with that one. Now we're going to define a different function of being the sine of x squared. So just like I did with the 2x, I'm going to replace every x in the original function with x squared. So x becomes x squared, x cubed over 3 factorial becomes x to the 6 over 3 factorial, and so on. Every exponent doubles. So even in the general term where I had x to the 2n plus 1, I now have x to the 4n plus 2. But nothing else in each of the terms changes, just the exponent of x. All right, now what I'm going to do is I'm going to find a series for g prime of x, which is the thing that I just found, and we're going to show that it's equal to the derivative of the sine of x squared. Now, if you took the derivative of sine of x squared, just remember you'd have to use chain rule to do that, and so you'll have to remember what chain rule is. So maybe make a quick note of what you're supposed to get for the derivative of the sine of x squared, and just make sure that we get there as we're going along. So this is what g of x looked like from the previous slide. So I'm just going to take the derivative term by term. X squared is going to become 2x. X to the 6 over 3 factorial is going to be 6x to the 5th over 3 factorial. So I'm just taking the derivative of the numerator and dividing it by the same numerical denominator, even in the general term. That 4n plus 2 comes down as a multiplier, and the new exponent is 4n plus 1. So that's the derivative right there. I noticed that with each term, I could factor out a 2x. And I'm doing that because I kind of have an idea of what the derivative of sine of x squared is. And I know that there's a 2x in there. So I am going to factor out the 2x so that the 2x becomes 1. 6x to the 5th over 3 factorial becomes 3x to the 4th over 3 factorial. So basically, every numerator coefficient gets divided by 2, and the x exponent gets reduced by 1. And so that's kind of what it looks like there. What I can do then is I can simplify each of the terms. So 3x to the 4th over 3 factorial can just be x to the 4th over 2 factorial. 5x to the 8 over 5 factorial can become x to the 8 over 4 factorial, and so on. And that looks like something I know. That should look like something that you know as well. That is actually cosine, but the exponents are twice as big as they need to be. So I'm just going to write each of those as x squared to an exponent that I want. So it's going to be x squared to the 2, and then x squared to the 4, and so on down with each term. That looks a lot like cosine, but with x squared instead of x. And that is the derivative of sine of x squared if I use the chain rule to do it. All right, different example. There's no x's in here. So x has clearly been replaced with a number. It should be a series that I'm familiar with. So let me just look at the patterns. It helps that I have the general term of this series that is 4 to the n over n factorial. And that looks a lot like a series we've already talked about. That's the Maclaurin series for e to the x. That's what e to the x looks like. And if you compare it to what we have, every x has been replaced with 4. In the third term, 16 replaced x squared. In the fourth term, 64 replaced x cubed, and so on. So it looks a lot like e to the x, but every x has been replaced with 4. So that means instead of having e to the x, I have e to the 4. All right. Similar, I have another series here. It's supposed to look like one that I know. I'm looking at the denominators and I see odd factorials, and I do also see that there is a sign change with every term. That leads me to believe that this looks a lot like the sine Maclaurin series, and that's what sine x looks like in blue, and it looks like every x has been replaced with the number 2. So instead of this being sine of x, if x is replaced with 2, then this is the sine of 2. All right, last one here. This is a little bit easier. I recognize this as just being a geometric series where a is 1 and r is negative 2/3. So I use my formula a over 1 minus r, plug in 1 for a, plug in negative 2/3 for r, and I'm going to get that the sum simplifies down to 3/5. All right, this is an interesting example because we have a power series. We don't know much about it. We do know that it has a series of constants a, k, but I really don't know what those are. There's no pattern or anything. There's just constants in front of x plus 3 to the k. The x plus 3 tells me that this power series is centered at x equals negative 3. So I need to keep that important information available. So I notice that the series converges if x is 2 and it diverges if x is negative 12. So I need to use my knowledge of the symmetry of these series to make a number line. So there's my number line right there. I've got negative 3 in the middle. I've got 2 on the right side, which is 5 units away. But remember, because of the symmetry of these series, I also need to remember that negative 8 is an important number as well. And then if I've got x equals negative 12 on my number line from the question, that's 9 spaces away from negative 3. So I need to include the number that is 9 spaces on the other side of negative 3 as well. And that's why the 6 is there on the right-hand side. Here I'm going to label the span of numbers where the series has to converge. And so if it converges at 2, then that means it definitely is going to converge everywhere from negative 3 to 2, but it's also going to converge on the other side of negative 3 by an equal amount. The only thing that I don't know is whether I can include that other endpoint of negative 8. So I know that it converges between negative 8 and 2. I know it converges at 2, but I really don't know whether it converges at negative 8 or not, just because it's an endpoint. And just because one endpoint makes it converge, that doesn't mean the other endpoint does the same thing. Similarly, I know that it might converge between negative 12 and 6 because it diverges at negative 12, but it could converge immediately after negative 12. And then that goes all the way to 6. And again, I don't know anything about that endpoint either. I know it might converge up to 6, but I definitely have no information about what's going on at 6. All right, so that makes it a lot easier to answer questions like true or false, or I think it's where it must converge, where it might converge, or where, stuff like that. We're figuring out what must be true, what can't be true, and what may be true. So if I put 10 on the number line, I notice that that's in my interval of things that might converge. So this might be true. I don't know. I would need more information to figure that out. The second question is the series converges if x equals 1. Well, that's within the interval of the numbers where the series definitely converges. So that must be true. The third part of this question is, does the series converge if x equals negative 8? Now, that is at the end point of an interval where the series must converge. But again, I don't know definitively about the endpoints. So that might be true. Then, if I'm asked about negative 9, that is within the interval of where it might converge. So that might be true. I don't know. And then the last one, the series diverges if x equals negative 13. Well, that is outside of the interval where things must converge and where things might converge. So if it's beyond that interval, I know that it definitely diverges outside. So that must be true because negative 13 is even outside of the interval where the series might converge. So it definitely doesn't converge there. All right, so the number line really, really helps. So do that first before you try and answer the can't be true, must be true, and might be true statements. All right, so last we're going to talk about derivatives and antiderivatives. I've got the function that's represented by 1 over 1 minus x. We know that that's a geometric series, so the Maclaurin series looks like that, 1 plus x squared, and so on. The interval of convergence, I mean, we already know that because we know what it is for geometric series. Your x has to be between negative 1 and 1. So, and you could plug those in if you didn't remember, but you'll notice that at the endpoints, the series diverges. We kind of knew that anyways. So the interval of convergence is between negative 1 and 1. So we're going to use this to find the sum of 1 plus 2/3 plus 3/9 and so on, n over 3 to the n plus 1. So let's find the derivative of that. Of the original series. So the derivative of 1 is going to be nothing because it's a constant. The derivative of x is going to give me my first term here of 1. The derivative of x squared is 2x, and so on. And those are the derivatives of x to the n. So what I notice is it looks like the series that they gave me looks a lot like the one I found for f prime, but it's just got 1/3 plugged in. So if I find the derivative of f, the function itself, and use chain rule to do that, I'm going to get that the derivative is 1 over 1 minus x squared. If I plug 1/3 into that, then I'm going to get a value of 9/4. So that whole series adds up to 9/4. Similarly, I could go the antiderivative route, find the antiderivative of that function f and use it to find the value of that series right there. So the antiderivative of f term by term, well, the 1 is going to become an x, the x is going to become x squared over 2, and so on. You know the antiderivatives of all those. And if I look at that compared to what I was given, it looks like the series I was given, but 1/3 has been plugged into that as well. So that means that this is the same as the antiderivative of 1 over 1 minus x, which is negative ln 1 minus x. And if I plug 1/3 into that, I'm going to get that this whole series adds up to the negative natural log of 2/3. So that is a lot of information, but I wanted to cover every possible question that you could be asked about power series. So if you have any questions, please let me know, and I will see you tomorrow.